In this tutorial, I will demonstrate how to visualize the results of the Monte Carlo simulation for net present value. Again, we generated 1000 net present values. We calculated 1000 net present values and would like to see how they look like. For that, we'll depict a histogram, and we'll construct a histogram of the newly generated net present values. The histogram, I would like the histogram to cover plus minus 4.5 standard deviations, because if it covers only plus minus 3 standard deviations, it may skip some of the outliers. So I'll start creating the bins for the histogram by first calculating the corresponding z-scores to the histogram. So let's say the average, it's going to be the center of the histogram, corresponds to a z-score of 0. And then I'm going to obtain the others by a step of half a standard deviation, or half z. Okay. 4.5, and then for positive, it's going to be plus half a standard deviation. Now these are the z-scores which correspond to the bins of the desired bins for the histogram. The center, or z-score of 0, corresponds to the average. Now I would like to reconstruct back the original values that will change every time we recalculate the Monte Carlo simulation. A z-score of 0 corresponds to the average, and then for the others we either subtract or add half a standard deviation from the average. Now these are the bins which will be updated every time the Monte Carlo simulation generates 1000 net present values. Here is a demonstration. I'll click F9 several times and we see how the bins are updated. Let's call the selection of bins bins. The next step is calculating the frequency corresponding to those bins. We would like those frequency to be generated dynamically. That's why we need to apply the frequency function, which is a block function. A block function is applied over a block of cells for all the cells at the same time. So this is going to be the area where the frequency function will be applied. We call the frequency function, and the first parameter is the data array, which is NPV random, and the second parameter, it asks for the bins, which is bins. Now we do not press Ctrl Shift Enter. We do not press Enter. We must press Ctrl Shift Enter. I repeat, we press Ctrl Shift Enter to apply the block function. And after pressing Ctrl Shift Enter, we apply the control function for all of these cells at the same time. Well, now we see that on whichever cell we click, there are brackets, which indicates that it's part of a block function. Now if we plot this frequency, this frequency distribution using a standard bar diagram, it's dynamic and it changes every time when I press F9, because it recalculates the net present values. But I would like to see a distinction between positive and negative net present values. I would like to be able to see where the positive and the negative values are. To do so, we need to separate the frequencies corresponding to negative net present values and the frequencies corresponding to positive net present values. To do so, we create two additional columns let's call them frequency positive, and frequency negative. In frequency positive, we are going to extract using the if function only the frequency if the net present value, if it is less than 0, then we do not want to see the frequency. Instead, we substitute with the NA function. If it is not less than 0, then we would like to see the frequency. And here, this function extracts only the frequency corresponding to positive NPVs, and for negative, the calculation is almost identical. We just need to consider the sign. So if it is negative, now we would like to see the frequency. If it is positive, we do not want to see the frequency. Here they are. Now we'll depict these two columns, and we need two of them because we want to assign two different colors for positive and negative, corresponding to positive and negative net present values. So now we'll depict, we'll plot these two variables using the standard column function. And we see that it already assigned some colors, different colors to the two variables. Now I would like to make the positive look green, and I would like to make the negative look red. I also would like to make the bars a little more substantial. And the final thing I would like to see is I don't want to see the I would like to see the actual bins, which are substituted by changing them in the horizontal axis label. Select bins, and here is the visualization of the results of our Monte Carlo simulation. We have only in this simulation only 0.6% of all values are negative in this scenario. We can lower the efficiency to demonstrate how the probability of losing increases with those initial conditions. Now, with those initial conditions, there is a probability 16.3% of losing money. Let's go to the initial conditions. 1.3, 0.7, going back to, it ranges between 1 and 2% as we discussed before. It will be interesting now to see how this visualization compares to the standard data table function, because the data table function, when visualized using conditional formatting, tends to mislead slightly the probability of losing money. So let's say I'm going to apply data table function here below the calculation of NPV. This is going to correspond to economy, and the smallest value for economy in our case is 0.8. It's supposed to range between 0.8 and 1.5. I would like to have 5 values ranging between 0.8 and 1.5 to make sure they are of equal distances from one another. We reconstruct those ranges by subtracting a quarter, because there are 5 of them. By subtracting a quarter of the range. I'm not going to focus on that too much. You figure it out. If we had, for example, 5, if we have 5 values, we subtract a quarter of the range. If we want to have 6 values, we recreate them by subtract a fifth of the range. Actually adding, sorry. Okay. And now we can see we recreated condition for we recreated 5 values for economic conditions ranging from 0.8 to 1.5, exactly those which are spaced equally from one another. If I change any of those, my values here also change and they're re-spaced equally again. So we do the same for economy, which is equal to 0.7 in our case, and we add a quarter of the interval to a quarter of the range to reconstruct the equal, so that those values will be equal from one another. Okay, now we see that it ranges between 0.7 and 1.3, and there are a total of 5 values equally spaced from one another. This will correspond to economy, to operation. And now this is going to be the area for the data table function. We insert the formula for net present value in the upper left corner, and I apply the data table function. For column input we have operation, for row input we have economy, and it doesn't matter that those are equal to something, because in the calculation of the table function they'll be substituted exactly with those values, not with the normal random function which we had before. I pre-formatted the data table function area before, and we can see now that if this was our initial analysis, it looks like about a quarter of all possible values, or a fifth of all possible combinations. The visualization indicates probably 25% chance of losing money, while when we consider the more realistic scenario, including normal distributions, this percent actually is 1.7. Let's make the conditions even worse. And in this case, we see that more than half, or about half, according to the data table function, visually it looks like there is a 50 or more than 50% chance of losing money. But according to the Monte Carlo simulation, we have a chance only of 35%. So the data table, the visualization of the data table function kind of provides a very conservative visualization for how likely it is to lose money. The net present value provides a more realistic visualization. So going back to the original areas, and this is what we get. Again, the data table function indicates about 20% chance of losing money, but according to the Monte Carlo simulation, it's only about 1.4%. And this whole thing was possible only because we considered or we assumed that the economic conditions and operation efficiency follow normal distribution, which is much more realistic.